This conference will now be recorded.
All right, Cliff, all yours.
Thank you, Bobby. Can you give me permission to share my screen? Thanks, and good morning, everybody. A couple things. I want to make sure everyone is up to speed on a couple things. Oh, it's not letting me share. All right, well, I'll go ahead anyway.
Hang on. I made you the
Try.
presenter.
It says
Yeah,
it's
it says you're the presenter.
Yes, it said that it's just having difference with the problem with the video conference. So, oh, maybe now it worked. It looks like, right? Yeah. So let's jump into it. First, everyone is aware that we approved the CDXML spec last December, and we are going to have a important announcement around CDXL that's going to go out on the morning of the 24th for everyone, and please look for that. It's going to be important for us to make sure that gets highlighted at the Chiplet Summit. Secondly, everyone should have received from Boppy a copy of the presentation that I have up on the screen here. That is an overview of the ODSA project. If you haven't, please reach out to Boppy, as he was supposed to send that out to everyone. And I would ask everyone to please take a look at it. It's very important that we're all on the same page in terms of our message at the Chiplet Summit if we get asked by anyone about ODSA and what's going on. And at a very high level, if anyone asks you about ODSA, I think it's really important to position the project as being focused on building an open chiplet economy and take people to and think about and talk about the open chiplet economy using this in your mind, that it's about establishing open marketplaces where chiplet vendors can provide chiplets to system and package builders and which get integrated and shipped to end users. And there's a support ecosystem that's needed to enable that. And the OCP is working to provide standardizations, different tools, prototypes, and analyzing workflows to help make that happen. And that within ODSA, there are 6 active work streams today looking at the business workflows, technical workflows in terms of chiplet description schema, a chiplet test bench, the way a benchmark criteria standardized for interconnect comparison, logical interconnects and physical interconnects. And we also are looking at launching some additional work streams this year. So very important from a messaging perspective, to make sure that everyone understands that ODSA is this much larger umbrella activity that the OCP is supporting. Now, secondly, one of the important messages that we're bringing forward is this notion that going down the road, chiplets will be everywhere across many market verticals, from automotive to communications, consumer, data processing, industrial, and others. And when it comes to solutions for each individual market, one size will not fit all. And if someone specifically asks you about a bunch of wires versus UCIe, that's the backdrop by which the message we want to take out is that there's room for multiple standardizations for different market verticals, and the market will decide for which market vertical is going to be the appropriate standardization. Now, I can tell you that Boppy and I have just spent a good part of the last 2 weeks, along with Jawad and Tony, and support from maybe one other who I'm not mentioning, and briefed 10 analyst firms on this message, getting feedback, and that this message has definitely landed pretty well with the people we've tested. So I'm pretty confident that this is going to be a good message to take out for ODSA and reposition ODSA as a much larger activity than it has been in the past. I'm going to stop here for a second in case there's any questions. Okay, well, please be cognizant of the message, and as you're all in some way engaged with OCP and ODSA, please be a bearer of the message. We will be using this message in the tutorial that is on Tuesday afternoon from 1 to 5. And Boppy will be leading off, and I'll be the, I guess, the person ushering everybody in and out. And we'll also say a few words about ODSA and what we're about. And then we'll have a pretty full afternoon where the intent is to bring together people in the community. It's not just a BOW tutorial. It's a tutorial based on the landscape. And in fact, some of the kickoff speakers, DJ and Amber, Amber from Google and DJ from Meta, while they are very supportive of ODSA, are also part of UCI, which is perfectly fine from our perspective. Other things around the Chiplet Summit, we do have our keynote on Thursday. We're the last keynote of the summit, which is a good position to be in because we'll have a chance to listen to everyone's message and to clean up in some respect. Please, if you can, come to our keynote, fill the room. The more people there, the better. And the other thing I wanted to mention was we had a request from some of the people that have booths at the show. By the way, OCP is booth number 33, and we will be there in the afternoon, Michael and I, and Boppy will provide some support for us as well. And we do have handouts. Some of the people who have booths there asked us for handouts. Michael and I will be bringing lots of handouts about OCP and ODSA to the event, and we'd be happy to share some with those that would like to have some of the handouts in their own table for ODSA and OCP. So that's it from me. Are there any questions that we need to cover in terms of being prepared for next week? Comments, concerns? Are we all good for next week?
So Cliff, just a quick question. So, for those of us who participate actively with the ODSA, when we're at the summit and I'm in charge of a couple of different panels and stuff, you want us to explicitly state our affiliation? I mean, is that what you're looking for?
Yes, we're looking for you to, if you're comfortable, to state that you're active and your affiliation with ODSA. We very much appreciate that. And if anyone asks you about it after the affiliation, it would be important that you'd be on message with us. The other thing is some people have indicated they would like to include a chart or two on ODSA in their presentation, which we would also welcome. And you're welcome to select from the charts that Boppy sent out.
Yeah, I know. I got the charts that Boppy sent. Thank you.
If that's helpful?
Yeah, no, that is. I just wanted to understand. I wasn't planning to use the charts, but I'm happy to state my affiliation and strong support for the team. So
thank you, Andrew. Important is if we state an affiliation, that after people might ask you, and so it'd be good for you to be on that. And just we're all
Nick here, same here, but our slides have already been submitted, so I can't go.
That's not a problem. If you can state the affiliation and speak to it, you don't have to show the charts. Okay, well, Boppy, I think that's it for me. Look forward to meeting everyone. Oh yes, and Michael and I will be there. And if anyone wants to have a chat with us about OCP business in any way, shape, or form, please let us know. We're booking meetings now for Wednesday afternoon and Thursday afternoon. Okay, Boppy, over to you.
All right, thanks. I'm going to spend 2 more minutes on. So here's a lineup. I think we've got enough to. I hope Taufik's back. I think we've got enough to devote February to just the business issues, business issues presentations from a bunch of companies. I've
I'm
got
back, by the way, Bobby. Thank you.
wonderful, wonderful. So I've got Ventana and Acronics for 2-3. No meeting next week because it will be all chipletted out. Kash and Michael on 210 from JSET. Mark, Kimberly, or somebody from Marvel allowed to pick. I picked a 217 as a Friday for them. Elad, I've slotted you in for 217 Friday, but in any other day, or somebody else from a nominee from Blue Cheetah. And Taufik, I've tentatively penned 224 for AMD.
Okay, I will confirm. Try to confirm today. I think it
Okay.
should work, and give you the speaker name and everything.
Perfect. And okay, so then let me bold you in. Then I'm looking. Who else am I like? Anu, Mitch.
I'm trying. I'm reaching out to folks, and in fact, you'll meet one of them at the summit. So maybe you can help convincing. So.
Okay. Anu, Mitch, Alan.
Boppy Nick here. On the
Yep.
AMD, I was at the Lindley Summit back in the fall, and there was a presentation by AMD on 3D packaging, or 2.5D 3D packaging, by the head of the packaging team. So I don't know whether he would be willing to do that here.
You mean Raja Swaminathan?
I believe that was, yeah. I'd have to go back.
Yeah, so
it's a different
Yeah,
gentleman.
we on the panel. Yeah,
it'll be
yeah, we're on the panel, right?
Yeah.
I'll find it. Anyways, but yeah, he did a really great job. So that would definitely be interesting.
Yeah, so I spoke with him, and I think it's going to be somebody on his team. But yes, we can bring him in, but I think somebody would do a great job also on his team.
Okay. So we will. I want to fit in 2 or 3 people on each slot. So if you all could please, I think I've missed a couple of other companies, but anybody who's interested in talking about their practical experience in selling with chiplets, we would like to hear from you through the month of February and organize ourselves.
Hey, Bappy, I wouldn't mind talking on a topic of OAM-sized substrates.
Okay, so let me slot you in for I think I'll aim for March 24th then.
That sounds good. Yeah, I'm flexible.
Thank you. So we've got a proposal from UCLA for a bow extension. That I'm going to tentatively do that. And then Benson Chan from Binghamton on packaging, which we were supposed to do in the new year, but I've sort of pushed it out.
Can you just put OAM site? Yeah, I see. I remember what I'm proposing.
Yeah.
OAM size substrates. Or yeah.
Okay.
Bob, entire roadmap is happening in February, end of February. Maybe we can ask Bill to share a readout from the HIR roadmap in March.
Okay. I think that's going to put us in 331. Okay.
Yeah, in March, late March. Or something.
Okay. So anybody else willing to give their company's perspective on business challenges with chiplets in February? All right.
So Bapi, you and I discussed about possibly either Rohit or Amber. So did you reach out or you want me to reach out?
Would you please?
Okay, I'll do that.
And I think I'm looking for somebody, people who try to actually directly either buy or sell chiplets and maybe draw from that experience, right? Right now
Yeah,
that
no,
that's
yeah,
the
true. That's more useful.
collection right now.
Yeah. Okay.
Any other names somebody can reach out to, like Tawfiq pinged internally to AMD? Any other names anybody's aware of that we should reach out to? Oh yeah, Tony
So,
or
Bobby Nick here. I'm going to talk about chiplet IP, not chiplet specifically. So I don't know what that's in
that's
scope
fine.
or not.
That's fine. That works. Either you're saying anybody trying to make money in chiplet IP, chiplet selling chiplets, chiplet tooling, you name it. With this, we would really like to gather everybody's thoughts in February. Okay. In that case, we're going to switch to our featured topic, which is the next generation of Bull. And oh, that's right, Marek. Okay, I know you're going to check offline. So I've got a collection of people: Marek, Anu, Alan, Mitch. Anybody else? If you want to volunteer, please let me know. But we'd love to hear from you in February.
This is Mitch. I didn't get a commitment from Shreyas.
Okay.
However, he will be presenting at the Chiplets conference.
Okay. And maybe we can get a summary version of something for this meeting.
There's a good possibility of that. I'll continue to pester him, so to speak.
Perfect.
Sorry, Bappy, what was the request? I missed that.
No, that if there's other companies you think who have practical experience selling chiplets and want to talk about it in February, now we would please reach out to them.
Okay.
Elad, it's all yours.
All right, hopefully folks can see the slides.
Yes.
Okay, great. So my name is Elad Alan. I think many of you probably know or familiar with me for Blue Sheet Analog Design. I'm essentially the technical lead of the BW sort of PHY working group and have been involved in ODSA in a number of different ways. In this presentation, I want to make it clear that this is representing the work of a whole bunch of folks over sort of a good period of time. And so I'm really just kind of summarizing all the great work that was done. So as Bapi was mentioning, we're really at a fairly stable point on BOW 2.0. We have like a punch list of I'd say maybe 3 or 4 items of things that still need to be edited into the spec. But otherwise, we're actually in very, very good shape there. So the purpose of the talk today was really to just kind of give you a few of the highlights on things that have been done, so you can kind of just get an idea of sort of what are some of the key improvements that we've made. There are a number of sort of let's say errata, ECN types of things that have just been fixes in other places. I won't walk through those here. So this is really kind of focused on the new features. I will say it's not like super detailed, but I have a decent amount of detail on sort of each of these topics. And sort of given sort of infinite time, I can probably spend sort of more than we have in the meeting here today on any one of them. So I'll sort of offer you in advance that if there's any particular sort of feature or topic that folks would like to focus in on first, please feel free to just sort of raise your hand, throw a throw a tomato or whatever it is. I'm happy to kind of jump around. The ordering here, to be frank, is somewhat arbitrary. So as I said, if anybody has a particular preference on, I really want to hear about, redundancy, even though it's at the end here, just again, let me know and I'm happy to jump there. So I'll just pause and give people a few seconds in case they already want to throw something out. And if not, then I'll just, start walking through kind of somewhat in order.
I think 32 gigabits per line would be great because that would just bring everything in line with CXL, I guess, in UCIe.
All right. Sounds good. Well, yeah, I guess I'll walk through that and then I'll give you some sort of meta commentary at the end, but sounds good. Okay. So basically from a spec development perspective, what I focused on here is just, all right, so what are the key things that we changed relative to the way we had defined some of the lower rates, to get to something that we believe, is fairly reasonable in terms of actually supporting 32 gigabit per second. So the first is just that the parasitic capacitance, particularly in the doubly terminated modes, does need to be sort of reduced, even further down to the around 125 femtofarads or so, whereas previously we were down around 200. And from sort of personal experience, there's kind of no way you get here without essentially having some sort of inductive peaking type of approach. So this is really something that is essentially only going to be doable in, let's say, in standard package types of bump pitches. So the 110 to 130, types of pitch. Once you're in essentially, the more tighter pitches that usually are associated with the more advanced packaging styles, there's kind of no way you can really just fit those inductors in there. The assumption is that in most of those advanced packages, you're probably doing, sort of source terminated rather than doubly terminated. So you can see that's why there's kind of this distinction here. But that, sort of the first kind of key critical thing that is done. The next thing is just, essentially the absolute amount of time it takes you to do things like, recover the clock, distribute it, add variable delay on it and things like that, probably isn't going to change all that much, even if you're sort of running the PHY at a faster rate. So just to account for that, we basically give more budget from a UI count perspective, but from an absolute time perspective, it's basically the same as it was in BO 256 in terms of just, sort of how you build the circuits that are able to do those things. The other thing we did is that we essentially halved the allowed, sort of absolute variation range on the transmit and receive impedance levels. The primary reason to do this is essentially just to make it so that you can always rely on the transmitter being lower impedance than the receiver. And this just basically buys you back some boost in the worst case signal swing, which obviously is, what we have to sign off against from a channel conformance and, compliance and et cetera perspective. The other thing, all of our specifications on the essentially transmit and receive circuitry from a timing standpoint are written as essentially percentages of the unit interval or the UI. And so kind of naturally things scale, kind of directly from an absolute time perspective as you scale up the data rate. But even with that, it does look like, and I'll show this in a moment, it is going to be fairly challenging signal integrity wise to really make sure we can hit those 32 gigabits per second in particular across a broad range of channels. And so we did actually tighten up the requirements on the receiver by 4% of the UI. It used to be 28%, it's now 24. So that's about a 20-ish% sort of tightening on the budget that's available there, specifically from a relative perspective. Again, the absolute, just scales directly with the data rate. And again, from experience, that is actually a pretty challenging thing to hit, in a high volume, sort of realistic operating condition. The final thing which we're doing a little bit differently than some of the other standards is we're just very explicitly saying, okay, if you're going to go at one of these higher rates, you do need to include a tunable receive equalization, specifically continuous time linear equalization, or CTLE for those of you who are familiar with that. We chose things specifically on the receive side because, in our experience, it's usually the lower power approach if you are going to include some form of equalization. This is not to say that people are not allowed to, sort of implement other things in addition to that. It's just that all PHYs must have a receive CTLE, and this is just to make sure that you don't end up in a scenario where two different vendors, like for example, one of them chooses the transmitter, one of them chooses the receiver. So, A talking to A's transmitter talking to B's receiver, that would be good because they both have equalization. But the other way around, B's transmitter to A's receiver, neither has equalization, and obviously in the cases where you need it, that would be problematic. So really the sort of, I shouldn't say proof in the pudding, but I think the most important thing out of all of this, besides just, okay, here's all the changes that were made, is some of the studies that were done to try and, sort of figure out, okay, well, is this really a feasible, sort of thing? And, what will it take? And, what types of channels look like they will support this well versus not? So we took kind of the bevy of channel models that we had available from our BOW 1.0 efforts, as well as a couple more that I just can't share publicly. And we essentially ran kind of a series of experiments and a series of sort of trade-offs to check, okay, are the decisions that we made actually going to result in things that are actually feasible? So there's a couple things I want to. Yes.
Sorry, I must not have been listening. This is for laminate?
That's a great question. All of these are indeed on organic laminates. Unfortunately, no one has yet provided a advanced package, sort of channel model that they were comfortable sharing publicly. I have done studies in the background, so I have, I do have data on those, but I just can't talk about them publicly.
Got it. Thank you.
So on that, bunch of wires 512, is that already, so that's 512 lanes, is that, I presume?
Oh, I see. No, I'm sorry. I should have clarified. Bow 512 just means it's 32 gigabits per second per line. So the 512 is just 32 gig times 16 lines.
Ah, right, okay. I suddenly thought, oh my God, 512 lines on the organic substrate. How
Yeah,
big is it?
Very good question. Yeah, so basically these rows here are just sort of, slightly different configurations. Really, it's unequalized with kind of all the specs that I provided previously, equalized with transmit FFE, equalized with a receive, sort of CTLE. This is all at 32 gig. This is all, it's 25 gig just for sort of, mathematical annoyance, reasons, but really it's 24 gigabits per second is what we're actually interested in here. But essentially just, again, unequalized and, two different forms of equalization. And kind of really the thing that I want to sort of highlight here is, there's some pretty interesting things that you can see happening. So first is, for example, if you look at, this full slice 2 millimeter and key site is about 6 millimeters long. If you look at these two, you'll actually see that in some cases, they're actually noticeably worse than some of the longer channels. So this one, 25 millimeters, obviously is 25 millimeters. All of these are around 20 millimeters of reach. You can actually see that in some cases, the shorter ones are good, but in other cases, they're actually much worse. And primary reason for this just appears to be essentially reflections on how they interact with crosstalk. And the other thing that's important to notice here is that, in those cases, actually turning on equalization, generally speaking, is a bad idea. Actually makes things worse, not better. Whereas in some of these longer channels where you really are starting to pick up, some degree of essentially loss in the direct lines themselves, that's where you can potentially pick up some degree of benefit from actually applying these equalization structures. So again, this just does really say that, you need tunability in that equalization, and obviously, sort of the complexity that comes with that. But that's sort of why it was specified that way.
So sorry,
yeah, go ahead.
I'm playing catch up here because you're talking out of my specialty. So is the first one no? I see FFE and CTLE. Is the first one no modifications?
Correct, exactly. So this is no equalization at all. This is sort of transmit equalization.
So in terms of cost of silicon and extra power overhead, the first one, I'd like to see power in here somewhere as well to see which is the most power efficient.
Yeah, no, it's a good question. So from a power consumption perspective, to zero order, okay, I guess I should be careful. To zero order, the least complexity thing to build is obviously not having any equalization at all. Right. Whether or not that turns out to be the lowest power on a given channel, obviously, is the question. Right. In the spec, we can't really say, sort of how much power X or Y is going to take. We can provide guidelines, obviously, but we do specifically sort of require the receive, continuous time linear equalizer, because in the experience of kind of, the designers involved in the development of the spec, that is kind of the lowest power way to achieve the equalization. And kind of one of the key points in the slide is that, there's a little bit of kind of tuning you have to do, but you can basically make it so the transmit, feed forward, and receive, continuous time end up with fairly similar performance numbers. So they're fairly equivalent from a sort of signal integrity perspective.
Okay. I guess I'm just I like to see the power. I don't really care how we do it. The power solution.
Yeah, I mean, actually, that's I'm glad you bring that up, and it's not explicitly written here, but our expectation is that you are going to pay a picojoule per bit penalty to be at these 32 gig relative to the 16 gig, at least on sort of the more challenging kind of channel conditions and things like that, and in realistic usage environments.
I think that's interesting. That's worth a dedicated slide for sure.
Yeah, and just to give you a sort of very rough ballpark, you're probably looking at if you can hit about a half a picojoule per bit at 16 gig, you're probably around 0.75 ish, at 32. So it's probably about a 50% picojoule per bit penalty.
Right, and across the top here, I don't are these just different pieces of IP?
These are just different. Yeah, these are just different packages. So this is a particular package design, at 2 millimeters length.
Design. Oh, okay.
Yeah.
So it's
so in other words, this is basically just a set of channel models that we have available under different conditions. Obviously there's a whole bunch more slides that I've jumped over here, but feel free to bug me and I can send you pointers for all those.
Okay, thanks. This is all public information for all these different packages.
Yep, absolutely. In fact, you can actually go download the channel models for all of these.
Okay, great, thanks.
Yep, absolutely. Yeah, so the other kind of meta point, just to help folks navigate these things, and maybe obvious because there's a lot of things that are kind of red. These ARM sort of channel models, the folks that had done these developments, intentionally did not apply kind of all the optimizations they knew that they could have applied to these models. Idea being, sort of trying to capture a reasonable common denominator of what people will typically be capable of doing in their designs. And what you can see is that, for sort of the deeper down layers, you're really in very, very bad shape, implying that, yeah, if you really want to run at these higher rates, you definitely have to be doing, quite a bit of, I should say quite a bit, but at least a reasonable amount of package optimization to make sure that these things really are feasible. Whereas at the 16 gig rates, most of these actually are pretty comfortable, they work just fine. So the point here being that, from a bandwidth density perspective, folks should expect both that, they do need to get, if they want to be at this full 32 gig, you really need to sort of, get the, sort of the A team from the package design perspective, as well as you might have to sacrifice some of the shoreline bandwidth density you would have expected from adding in extra, sort of power and ground shields and things of that nature.
So on this package design, do you think this is worth the actual package design being fully in the open community?
So actually, yeah, I mean, there is one, or actually maybe even 2 or 3 now. So there's a couple of folks that, actually shared those. I believe AlphaWave had done some of the early work and shared that, which I believe is, just out on the Google Drive. There's the so-called interop package that has been done to look at essentially, sort of D-Matrix and Blue Cheetah sort of PHY interop. This is a 1.0 thing, but I believe that package design is also, sort of available in the open. So yeah, so there definitely are sort of, references that are out there. I suspect that, some of the 32 gig things, people may or may not, sort of be as willing to share, but generally there are definitely designs that are out there. And, and some of these techniques,
another question, I'm just discovering that, well, obviously it's been around for a while, but the 3D, the substrate build-up approach, like a 3D printed approach to laminate or PCB structures is gaining traction. And I've heard there's a new one on the market, I don't know how real it is, where they can get down to 45 micron line in space, and you 3D print it, so you can actually get higher topologies. Are you researching those and actually modeling those as substrates and how good or bad they are for this type of thing?
Yeah, so I'm not 100% sure. There are things that I've heard of and looked at, that are similar, exactly what you described, I'm not sure. So yeah, so if you have any pointers or, sort of models or things, we're happy to evaluate.
Yeah, I guess this gets to the topic I mentioned to Bapi, is I'm thinking, when I look at the signal integrity, and I'm talking about standard PCI channel or Ethernet channel, where we're trying to drive 30 dB. If you look at the way IEEE allocates it to people, it's like, well, we're going to give 5 dB to the package guys, or because we know the worst package guy needs 5 dBs, but the best package guy only needs 2 dBs. And then you look at OAM, then if you look at OCP, it said, well, here we go, we've got this entire module, we're going to give you a total of 8 dBs to get to the connector on the baseboard. And that 8 dBs is made up of, well, we got to give 5 dBs to the package guy because he needs that, because the worst package is going to be 5. And then we're going to give you 1 or 2 dBs for the trace and 1 or 2 dBs for the connector, and that's where the 8 came from, right? And it's like all the worst case scenarios are being added together. And if you look at it, we're now trying to put all these chiplets inside the package. Look at the package sizes. Look at our AMD's EPIC package. It's actually epic in size. and they're up to 100 or by 100 now. They're not far off from an OEM module. And the OEM module really only adds power supplies and a bit of sideband circuitry. And so, hang on a minute, why don't we get rid of the package and use the OEM module as the package? And then everyone says, well, hang on a minute, you can't do these fine lines and traces, because they're, so substrates are really struggling. But there are certain rules you can do on the substrates. And then if you look at this 3D build-up, maybe the substrate.
Yes, Alan, sorry, can I pause you for a second? I mean, this is all very, very interesting. There's definitely a lot more to go through here. So if you don't mind, maybe we'll continue and would love to have a discussion. No problem. Thank you. Okay. So, if there's more questions on the high rate stuff, obviously feel free to yank me back. But just, sort of moving forward,
Hey, Elad,
Oh yeah, of course.
just the one, it's not something unique to Bo that makes you have package design, a better package. Anybody going at 32 will need to pay attention to the package design, right?
How should I say it? I believe the answer is yes. I would not want to claim that, like, I have, literally simulated every single possible combination of designs one can come up with. So, so if somebody wanted to be pedantic, you could make that argument. But, in practice, I think the answer is yes.
Okay, thanks.
Okay. So next sort of, next major feature I want to talk a little bit about was just on the power management side. So here in particular, our goal is to essentially define two specific additional power states besides just, sort of the link is up and active. I'll kind of walk through sort of, a little bit more of those details, but essentially those two states are that the clocks, particularly the forwarded clocks, remain active, but the data is idle. And the other is that both the clocks and, the clock is gated and the data is idle. And you may be wondering, well, what the hell why do you care about a data idle state? Well, it turns out that, if you're looking at terminated signaling, then essentially about 30% of your power at 16 gigabits per second is probably being spent on the transmitter and receiver. This number was, sort of surprisingly consistent across the vendors that we polled. For 8 gigabits, you're probably saving about 43% of the total power. So the point here is that, if you're doing terminated signaling, sort of, putting yourself into the state where you're not burning the termination power actually has a noticeable impact. It's not, factor of 10, but it's pretty noticeable. And obviously, if you're doing unterminated signaling, this doesn't really do anything. You're just not creating any extra transitions. You would have been toggling anyways, but but that's okay. It doesn't harm anything there. The clock's gated and data idle. This is where really you sort of have a much bigger opportunity to save, sort of significant amount of power. Easily, sort of 40 to 50%, and often cases, sort of even more than that, depending on how aggressive of an implementation you take. Both of these are so-called fine-grained states, right? So these are entry-exit latencies of like quote unquote zero. If it's data idle, it's literally just you send basically all zeros on the data lines, to something like 1 to 2 nanoseconds of entry-exit from the clock-gated states. Exact numbers there again, kind of being somewhat dependent on rates you're running at, and some of the other details that I'll touch on in a moment. So one of the key sort of design goals we had here was essentially how do we do that without sort of essentially forcing significant penalties on peak power consumption, bandwidth density, meaning like the number of wires you need, or sort of the overall complexity of the implementation. And I think we actually sort of threaded that needle pretty well, but let you all judge that as I kind of go through more of the detail. But it is sort of important to mention that all of these features are entirely optional. So people would just say, yeah, we're not building these things. We just always operate in a continuously active mode, and that's totally fine. Okay, so this one is very short because it is a very simple thing to do. So if you want to be clocks active and data idle, basically we're just going to define that if you put zeros on all of the data lines, including an aux and FEC, if you use them, we're sort of conceptually defining that to mean quote unquote data idle. And in some senses, the PHY itself doesn't even really need to know about this. It's really just that the link layer and above, they basically have to control the data so that if they know they're not really sending something valid, just send that as all zeros. So really, this is kind of a PHY implied requirement on the link layer and usages above. So the next state is, the clock gated and data idle. And obviously this is where things, get much more interesting, both from a power savings perspective, as well as from a kind of, just complexity to actually implement it. So, just to kind of sort of walk through some of the definitions here, so when you are essentially in that clock gated state, it is the case that, you essentially have to be sending a data idle, kind of, hopefully by definition of the name. To simplify some of the clocking considerations, we do actually send a valid clock value across on the differential clock during that idle period. You'll see sort of more detail about this in a moment, but following what I'd say is, sort of best practices from many other places, you do enter and exit these states essentially with both pre and post ambles. And essentially sort of the entry and exit on the transmit side is controlled by a new link layer interface signal that we call PHY idle. So essentially the, sort of the link layer indicates to the PHY, okay, you're going to be entering idle sort of at a particular point. And when that happens, that's when you gate. And essentially, once it brings that signal low, then it says, okay, on the next, quote unquote parallel cycles when you exit it, that will also cause a preamble to be sent and so on and so forth. Now, I do want to mention that, sort of the control happens entirely on the transmit side. The receive essentially sort of knows, quote unquote, knows whether it's idle or not, only indirectly by essentially having the clocks being toggling or not. So in other words, kind of a lot of what this is engineered around is to just keep the receiver very simple, not necessarily require that it has, sort of an extra data line or some other sort of circuit that, sort of figuring these things out. You can actually just build it in a way that effectively that forwarded clock naturally gates all the behavior on the receiver anyways. And that's again sort of in this goal for overall simplicity of implementation. So that is part of why we specifically state the clock remains valid even when you're sort of in this clock gated mode. This does mean that if you're in terminated operating conditions, you will actually be burning some power to just sort of drive the clock minus line high. If you're since your receive side is intended to be terminated to ground in this case. So there's a few milliwatts that you'll burn just from doing that. But typically that's a reasonably acceptable floor given that you're usually doing these terminated things at the higher operating rates, 16 gig plus. So you're kind of comparing about 5-ish milliwatts to usually 100 to 200 or something like this anyways. So there is sort of a very good dynamic range ratio of power there. And it turns out there are implementation techniques sort of advanced vendors could use to try and knock that down further should it turn out that that is something that's interesting or needed. Okay, so just to kind of give a few more details here, and the pictures, at least for me, helped a lot to kind of understand what was going on. I won't necessarily walk through them here, sort of in a lot of detail, because I really just want to kind of hit some of the highlights. But essentially, we, as I said, we do insert a preamble, we do insert a postamble. We essentially quantize both the preamble, the postamble, and the kind of width of the active data packets to what I'm going to refer to as a parallel width word. So what I mean by that is, in both the transmit and receive directions, there's some degree of serialization and or deserialization, serialization and or deserialization that's done. So let's say, for example, you're at 16 gigabits per second, but the rest of the world is operating at 1 gigahertz. There'd be like a 16-to-1 ratio there. What we're basically saying here is that you have to essentially quantize the essentially time durations of all of these sort of units of operation into units of 16 UI. So the reason we do all that is that essentially if you sort of at the beginning of time have brought everything up, figured out parallel word alignment, meaning sort of framing, if you sort of prefer that term, meaning where which bit is really like bit 0 out of the overall 16 bits in that previous example that we talked about there. Then essentially once you've done that, if from there on forward you always use quanta that are aligned to that, you never have to worry about resetting sort of that whole framing operation. And that's kind of a nice thing to have because otherwise you might have to sort of either take some extra latency to set that up or forward an extra data line across, which in both cases those are things that we really did not want to have to deal with. The other thing that again I think is just sort of borrowing best practices from sort of folks that have done similar things in the past is that we're defining a maximum gated duration, meaning that the PHY is not allowed to be in the clock gated state for too long. In particular, sort of the minimum of 1024 UI or 128 parallel words. In other words, whichever one of those is shorter. And basically, this is just to make sure that all these things like duty cycle correction loops and delay lock loops and things of that nature, that essentially they never have to worry about being off for some arbitrary unknown amount of time and then immediately being turned back on and expecting to be working. Essentially, this just sort of does these keep alive bursts that will come through and make sure that those loops can continue to operate and continue to be refreshed so that you never sort of have to worry too much about them drifting away. So I realized I sort of ran through this very, very quickly. I'll just pause and see if there's any questions on this part. All right, Boppy, I'll just check you're still there as my yes man for this one.
I'm forever your loyal yes man. Yes.
All right, sounds good. Okay, so just pushing forward, on some more of the features. Another one, which I think is actually, sort of quite interesting for some subset of markets, is the so-called half-width slices. I want to just, sort of give some credit where credit is due. As at the beginning, really all of this is a result of a lot of work by many folks. But there's, sort of specific folks that really stepped up and took the lead on particular aspects. Mark Hempel gets really the credit for this one. So the idea here is that there are definitely applications that that folks are aware of and are potentially even working on where they've seen that there's a very stringent requirement on essentially, just the absolute size of their chip needs to be, for example, less than 1 millimeter. And if you want to use sort of a low cost packaging technology, with a minimum of 16 data lines plus forwarded clocks, and you want to do kind of like transmit plus receive, you kind of like couldn't fit into that footprint. So the idea here is that, if you essentially just say, all right, well, if I really physically have to fit in this very tight footprint, let's go and define a half width slice that essentially has only 8, actual data lines that you're carrying rather than 16, and essentially just, allow people to physically fit into that size. There are actually some other cases where, you kind of like want to optimize the last little bit of, sort of quantization of your data bandwidth relative to kind of your bandwidth needs, this could help with as well. This is also just sort of a way of saying, well, look, I really have an overall net very low bandwidth requirement, so I really, sort of don't need all these extra data lines. Something like a sensor or data converter, things like that, that also is sort of a motivation for doing something like this. I do want to say that it doesn't necessarily have to be only low bandwidth. However, we do define that you can stack these half width slices. You're only allowed to stack half width with half width, not, sort of have things, with a full and a half. At least from a sort of, spec perspective. And that was mostly just so we didn't have to worry about kind of figuring out all the interoperability cases. And I do want to say that kind of the general approach that we identified here can be extended to even lower widths if one wanted. But again, just to sort of, avoid combinatorial explosion, we only defined explicitly the half width, formally within the standard.
Can you remind me, a normal slice
is 16 data lines.
And that's only one direction, so for bidirectional you need 2 slices, is that correct?
Correct. Yes, that's right. Yep. Great. So for those of you who are eagle-eyed, you might notice that this is kind of arranged in a slightly different way than you might have first expected, meaning that the clocks are kind of off over here on the side and the data lines are on one side of it. The reason for that is really this picture, which was, okay, we still believe that it's likely people want to be able to interoperate between sort of half slices and full slices. And so what you can kind of see here is that essentially we just explicitly went in and eliminated the upper sort of halves of these data words. Idea being that if you have a half slice talking to a full slice, you can actually just directly wire 0 to 0, 1 to 1, 2 to 2, and so on and so forth. The reason you usually put the clock in the middle is to try and keep the skew between the clocks and the data lines as small as you can. But if you think about it, if you were able to build sort of the full width slice and these skews are sufficiently small, you could actually do the same with the half width slice as well. And this just then simplifies the interoperability in this particular case. I just want to point out, the FEC and the aux are still sort of optional, but they're sort of placed kind of in the spots they would have been, let's say, from a quote unquote logical ordering relative to the full slice, again, for kind of the same reason of, it just allows us to kind of wire things fairly directly, in the interoperability case without having to worry about, sort of swizzling and, reinterpreting of data and so on and so forth. And really from an electrical, sort of performance standpoint, it's the same skew as you would have had in the full slice. And since we don't think that was sort of like the critical driver overall, for most cases of getting the full slice working, that's why we sort of did this slightly non-intuitive non-intuitive initially approach. But overall, we think this actually works out quite nicely.
Ela, the sort of off topic on this, but one of the things we noticed yesterday in the PHI meeting, or the link layer meeting, excuse me, is that we probably need to develop an ODSA glossary so that all the terms are defined in a consistent and common manner across all our specs. So I'm going to reserve a meeting in the future for that. Across all our work streams, that we use the word slice, link, package, or whatever to mean roughly the same thing.
Yep, no, totally agreed. Okay, so just soldiering forward, and we'll see how many of these I get through. The next one that's just on the agenda here is so-called sideband slices. Kash, I wanted to give credit myself or the ones who probably primarily took the lead on this. So you might be asking, well, okay, like, what are you really trying to achieve here? Like, why do you have to define this thing separately? Really, the main motivation behind this was that there are again applications that were of interest where essentially the boot up or reconfiguration time may be fairly heavily constrained, and in those cases you might need higher bandwidth, kind of essentially sideband, meaning from a transmit from one chiplet to the other chiplet, but that doesn't require any kind of configuration. You might need sort of higher bandwidth signaling than, for example, something like what my I3C would be able to provide. So the goal here is to say, okay, in those cases, we want to have sort of a method that we have defined that people can use as a PHY to carry this kind of data traffic across it. And so this sideband slice is essentially something that is defined to carry up to 1 gigabit per second of data payload. Again, this is an optional thing. You can choose to use it, you can choose not to, but it is fully now specified in the draft spec. So as I kind of implied at previously, the key distinction here is that they sort of have to work immediately out of reset without any kind of extra configuration, because obviously the whole point is that you're rather without any kind of like training or something like this, exchange back and forth, because the whole point is you use these to actually bring up and train the main bands. And B, since this is intended to be a control channel, and you most likely don't want to have to deal with excessive error correction or things of that nature, or retries, it is spec'd all the way down at 1e-25 error rate. As a side note, if anyone sort of has data or insight or thoughts that they want this to be lower, higher, etc., please do feel free to reach out. This is a fairly insensitive parameter, but we sort of chose that based on our current predictions and understanding of where current systems are likely to end up with from a net kind of control traffic throughput, and this seems to be a pretty reasonable spot to be at. So just kind of unlike the main band slices, there's only a single data line. So there's essentially a single-ended, I should have written this down. There's a single-ended forwarded clock. There's a single data line. There's an explicit, sort of additional line for essentially a framing signal, so that you never have to worry about sort of figuring out what the quote-unquote parallel word alignment may be. In other words, you always have a marker that you can use to figure out sort of what bit 0 actually is. And essentially, the forwarded clock is single data rate, meaning that we launch on rising edge and capture on negative edge. So you don't need anything like a DLL or sophisticated receive training. You can basically just have intrinsically the edges you need to be able to recover things with pretty good timing margins.
Excellent. So is that three? Did I hear 3 signals there then? The clock,
Yep, that's right. It's 3 lines, and you can kind of see it over here. This is kind of like what the sideband footprint would look like. So essentially, I also forgot to mention, sidebands are always bidirectional. So there's a read data, a read clock, and a read framing signal. Then there's a receive data, receive clock, receive framing signal, transmit data, transmit clock, transmit framing signal. This is kind of the sideband module, or excuse me, sideband slice.
Okay, nice.
Yep. These are all, you don't have to do it this way, but we definitely recommend, especially in bandwidth constrained applications, you place them behind the main band. And the idea here is that, that it's essentially not going to eat into your shoreline if you do it that way.
Hey,
this also, yeah, of course.
Sorry. We're going to lose people at the top of the hour. I think we can run over, but if we want something, maybe you can cover it in the next 3 minutes and then go to the slides themselves. I've sort of penciled 310 for an updated version with feedback.
Yeah, no problem. Yeah, I don't know if there is somebody who really wants to hear about bidirectional slices, redundancy, or anything else. Feel free to throw it to me. I don't know.
We want a review from anybody who's interested over the next 3-4 weeks. We have a stable draft, etc. Right?
Oh yes, thank you. Yep, thank you. Maybe go ahead. You can,
Elad, would you be able to share these slides with
Yes,
the group?
no problem.
Okay, appreciate that, because we might have additional questions.
Yeah, for sure. Absolutely.
I think timeline-wise, we have a stable draft at the Git repo with even the version numbers correct. Miracle be miracles. And so we would appreciate anybody who has technical feedback to generate it in February, so that we have a stable draft. We have a near final draft by the first week of March. Is that fair, Elad?
Yeah, no, that's totally feasible.
So if you or anybody in your company who's willing to review it, please share feel free to share the Git repo link, and we'll take all feedback.
Yep, and if anybody has questions, I'm both happy to share these slides. There's sort of a bunch of material and things from kind of the working group meetings that obviously are behind both of these and what's in the spec. So happy to share those as well. Feel free to just reach out to me. Okay, so maybe like in the 3 minutes or whatever before the hour, and then if folks are available, I'm happy to continue. Yeah, just to kind of wrap things up here, the idea is that you'd put these sideband slices, quote unquote, behind the main band, and so that they don't necessarily also increase your package layer count, at least not directly. We kind of expect that most people would essentially route these sideband signals underneath the core layers. So for example, let's say you had 525 stack up, and you were using that to basically do two deep stack of main band. you'd probably take these sidebands and run them, sort of down, somewhere below, like, essentially layer 8 or down. And so, in fact, we do actually have a representative, sort of package design that was done with this. There's actually the interop package design just taken and kind of modified to hypothetically include sort of a sideband slice, sort of behind somewhere. And you can see, it was actually routed, connected together. Kind of the point here is you can see it's, sort of making its way down from the top layer, through the core vias, routed across, and then obviously symmetrically up on the other side. This channel model was actually used to then do a bunch of detailed signal integrity simulations, and come up with kind of the detailed electrical specs. So one thing I really want to highlight here is that even though this is a sideband, it's a real PHY. It has all the real PHY requirements, sort of explicitly spelled out. So there is, I think, our intention there was to make sure that there really is a good sort of confidence in electrical interoperability and sort of a broad range of channel conditions actually working. Because even though it's sideband, it doesn't come for free. You got to make sure that things actually work there. Great. So the last two I've got, which I think both are fairly short, so I'll see if I can rocket through them. And again, if folks have comments, questions, want more details, feel free to stop me here or afterwards. So we did go through and sort of also do definitions of what a bidirectional slice would look like. Again, credit for leadership here goes to Ken Polton and Shahab, Ardalan from Luminous, Ken from Keysight. So here, essentially, I don't think there's anything kind of too surprising, other than that there are some number of details one has to work out and just sort of explicitly write out in terms of how it is that you want to handle potentially slices that have the capability to work in one direction or the other. And again, sort of picking up learnings here from a lot of prior work that was done in many different groups and standards. And so it is all actually explicitly written out. Both these pictures are taken from the spec itself. I do want to sort of clarify the intention here is that essentially, this is intended to be sort of like a slow configuration thing, right? So technically you can, sort of quote unquote runtime turn the bus, in the other direction, but you do that sort of after a full reset of the interface. There isn't anything that sort of reasonably dynamically or reasonably fine-grained turning things around, at least for now. Largely driven, to be frank, by that we didn't have sort of many people that felt that there was a strong application for need that just yet. But again, if there's interest, this is definitely something that can be sort of expanded upon further, moving forward. Okay, so just last topic, on the redundancy side, this was largely led by Greg Favor, myself, and actually, Kash and others from Etopus were also involved. Okay, so this one, sort of to be frank, I think kind of, for many of us who are doing 1.0, we all sort of, kind of said, okay, yeah, like, clearly we can do redundancy and, there's some fairly obvious ways we would do it. But we did want to make sure there was a clearly specified and agreed upon method for doing so, sort of written out in the spec, just to make sure interoperability wise that, people are making consistent decisions. And so, again, the obvious thing to do here is that we essentially take the optional aux and FEC bumps and just say, okay, there's no aux and FEC. Instead, we're just going to use them as redundancy. So in other words, for every essentially 16-bit data bump, 16-bit slice, we now have actually a full 2 bumps of redundancy. So we think that's actually, sort of more than enough to, sort of cover for a large variety of manufacturing variations or manufacturing issues. However, there is one sort of key optimization we did, which some standards do this and others don't, but we think is really an important one, particularly for the very high data rates, which is essentially saying that we will support redundancy only on the data bumps and not on the clock bumps. And the reason for that is just that essentially the circuits you have to build to essentially kind of deal with redundancy on the clocks, look quite a bit different and somewhat more complicated than if you really just have data redundancy that can, in principle, just be a whole bunch of muxes in the digital backend. Whereas if you're trying to mux a clock, it kind of has to be an analog mux because you're using the clock to recover the data or send the data, as the case may be. So that's why sort of things aren't quite as straightforward there. And I should say that, from an overall yield perspective, since it's, the clock bumps are only 2 out of, a much larger number, from a net yield hit, as long as the errors are random in nature, this is a fairly small kind of overall impact. So the other thing that was, just a little bit interesting, you can imagine there's many different ways you can potentially use, sort of this 2 bumps to kind of create redundancy. These are just sort of 3 sub-examples, but, in particular, the one we chose is the so-called ungrouped one, where essentially if any particular data bump is broken anywhere or any 2 are broken anywhere, you essentially always shift down from the lowest one that's broken. In other words, let's say D3 was broken, you just shift everything down, and D0 would become, aux would become D0, D0 would become D1, so on and so forth. And let's say, for the sake of argument, D9 was broken, again, you'd shift everything up, to go into FEC. I happen to have chose things that were on either side of the clock, but it doesn't have to be that way. Essentially, you just have full flexibility for whichever the data bumps happen to be broken. You either shift up or shift down depending upon its relative position. So this is stating that basically means you need like a 3-to-1 mux in the digital backend for essentially all of the bumps, with only a couple of exceptions. So you may be wondering, well, it seems like you could have gone with one of these other ones and they're, maybe slightly simpler. Maybe they only do like a 2-to-1 mux. The main reason for that is that as soon as you have a signal-to-signal short, you basically are guaranteed to have 2 bumps that really are broken, as opposed to, for example, just one in a particular location. So this one really handles, sort of that in the most graceful fashion. And especially with that optimization we did of, not doing redundancy on the clocks, it is a fairly straightforward thing to do in the implementation. So that's why we went ahead and chose that. Okay, so I think I leveraged my ability to rocket through all this, sort of fairly quickly. If there's any questions, please feel free. But we're at 4 after, so I'm also happy to just call it a wrap here.
This sounds like it's trying to align with UCIe. Is that the objective?
Yes and no. There are some things here that that are fairly similar. There are some that are I'd say quite different for various reasons. I guess since since I can't really comment in a lot of detail on the internals of UCIe, I'll maybe leave it at that.
Okay. Very good, by the way.
Great, thank you.
Okay, so if you have comments, February is it. We are looking to clean it up based on any form, but not that we expect a lot of cleanup, but review is always good. So February would be getting your feedback in February would be very helpful. Elad, thanks for putting this together at short notice.
Sure thing, my pleasure.
Okay, in that case, everybody have a good weekend. Thanks for staying over. See you all next week.
Thanks, everyone.
Oh, actually in 2 weeks. See you all in 2 weeks,
Right.
but see you all in person.
Thank you, everybody.
Thank you. Bye.